Hello and welcome to SigmaXL video tutorials. This is part 1 of the Introduction to Time Series Forecasting videos. A time series is a series of data points indexed or listed or graphed in time order. Most commonly, a time series is a sequence taken at successive equal spaced points in time. Time series analysis comprises methods for analyzing time series data in order to extract meaningful statistics and other characteristics of the data. Time series forecasting is the use of a model to predict future values based on previously observed values. SigmaXL provides the tools and methods shown for exploratory data analysis and time series forecasting. SigmaXL also includes control charts for autocorrelated data, which will be covered in a later video. Please refer to the workbook in Part J of the Control Phase section for recommendation on when to use particular methods. For this video, we'll be focusing on the following tools in SigmaXL: autocorrelation function plots, seasonal trend decomposition, and exponential smoothing forecasting. The main feature of this video is exponential smoothing. The ARIMA methods will be covered later in this video series. I'll be using a sample dataset called Chemical Process Concentration, Series A, which is the Series A data from Box and Jenkins. It is a set of 197 concentration values from a chemical process taken at 2-hour intervals. We will now do some exploratory data analysis of this time series example, starting with a run chart. Click SigmaXL, Time Series Forecasting, Run Chart. Select Concentration and click Numeric Data Variables Y. Select Show Mean and ensure Non-Parametric Runs Test is unchecked. Click OK. Clearly, this is a non-stationary process with a wandering mean, which exponential smoothing can model. Just as correlation measures the extent of a linear relationship between two variables, autocorrelation measures the linear relationship between lagged values of data. ACF denotes the autocorrelation function plot, sometimes called a correlogram, which is a bar graph of correlation values. PACF is the partial autocorrelation function plot. For further details and formulas, see the appendix of the SigmaXL workbook. Now, I'm going to demonstrate how to create the autocorrelation plots manually. These graphs will be created automatically later in this video. We'll be using the lag utility and scatter plots to demonstrate the linear relationship between lagged values of data. Click Time Series Forecasting, Utilities, Lag Data. Select Concentration and click Numeric Time Series Data Y. Ensure number of lags is set to 1 and click OK. Here we have a new sheet created with lag 1 data. Click Recall SigmaXL dialog menu, enter lag equals 2, and click OK. Repeat for lag equals 3. Click Graphical Tools, Scatter Plot Matrix. Check Use Entire Data Table and click Next. Select all 4 columns and click Numeric Data Variables, Y. Ensure Display Trend Line is checked. Click OK. The scatter plots for lags 1 through 3 are produced, which show a positive trend. This also means positive autocorrelation. Select the Lag Data Sheet tab. Click Statistical Tools, Correlation Matrix. Select all 4 columns and click Numeric Data Variables Y. Clicking OK will provide the correlation coefficient matrix. With a lag 1 correlation of 0.57, lag 2 of 0.5, and lag 3 of 0.41, and with the correlations in red, this matrix is indicating that the correlations are significant. Here we've manually calculated the correlation coefficients. We will now create the ACF plots, which calculate the coefficients automatically and display them as a bar graph. To create the ACF plots, click the Sheet 1 tab. Click Time Series Forecasting, Autocorrelation ACF PACF plots. Select Concentration and click Numeric Time Series Data, Y. Use the default automatic number of lags. Seasonal frequency equals 1, alpha level equals 0.05. Clicking OK will produce the ACF and PACF plots. Hover the mouse cursor over the lag 1 ACF bar to view the correlation value of 0.57, lag 2 of 0.5, and lag 3 of 0.4. These values are approximately the same as those obtained manually, with some minor differences in how the correlations are calculated. The lags that exceed the significance limit lines are statistically significant at alpha of 0.05, so there is an autocorrelation structure in the data which can be modeled using exponential smoothing or ARIMA, but we will focus on exponential smoothing for this video. In the next segment, we will take a look at trend using seasonal trend decomposition. The seasonal trend decomposition plots are useful to visually distinguish trend and seasonal components in the time series data. If the seasonal frequency is unchecked, a trend decomposition plot is produced as the first chart, showing the raw data and the trend. The trend component uses data smoothing rather than a linear trend so that it may display either a linear trend or cyclical patterns. If a seasonal frequency is specified, for example, monthly sales data or quarterly revenue, a seasonal trend decomposition plot is produced, showing the data, smooth trend, and seasonal component. This will be demonstrated in a later video. Click SigmaXL, Time Series Forecasting, Seasonal Trend Decomposition Plots. Select Concentration and click Numeric Time Series Data, Y. Ensure seasonal frequency and Box-Cox transformation remain unchecked. Click OK. As discussed earlier, we can clearly see the wandering mean in this process, but with a smooth trend line. This is an additive decomposition model, so the sum of the trend value plus remainder value gives the original data value. We'll be modeling this using exponential smoothing next. Simple exponential smoothing forecasts are calculated using weighted averages, where the weights decrease exponentially as observations come from further in the past, with the smallest weights associated with the oldest observations. This is also known as the exponentially weighted moving average, or EWMA. Weights for different alpha values can be demonstrated graphically. An equivalent formulation for simple exponential smoothing is shown, with the starting forecast value, the initial level, Y1, to be estimated and denoted as level L0. The smoothing parameter of alpha and initial level L0 are determined by minimizing the sum of square forecast errors, residuals. Now, to demonstrate simple exponential smoothing, I'll use an Excel template in tandem with Solver to perform the calculations before using the automatic calculations in SigmaXL. To begin, open Demo of Simple Exponential Smoothing, Concentration. This is the same Series A data from Box and Jenkins, a set of 197 concentration values taken from a chemical process at 2-hour intervals in column B. Clicking cell C2 in the one step ahead forecast column, we can see that it's the initial level, which is given in cell C4. C3 is a forecast formula. Cell D3 is the actual minus the predicted. Cell G3 is the alpha smoothing parameter value. Cell G4 is the initial level. These may be manually entered or solved using Solver. Cell G7 is the residual sum of squares error and is the value to be minimized in order to produce the most accurate one-step ahead forecast. The exponential smoothing model statistics are also given for later comparison to the SigmaXL report. The equations may be viewed by clicking on the demo cells M5, M6, M7, or M8. The raw concentration data are the black dots in the graph. The one-step ahead forecast values are the red dots. Before using Solver to determine the optimal alpha and initial level values, I will demonstrate how the graph changes when manually entering values. With an alpha of 0.01, we can see that the small value of alpha produces a smooth fit with SSC, which is equal to 31.02. That is larger than what we started with, 21.83. A large alpha value, for example 0.99, results in approximately a naive forecast, with the one step ahead forecast value equal to the previous actual. With an alpha of 0.1 and initial level of 20, we can see that this initial level is a poor estimate of the start value and results in SSC equal to 71.02. After about 30 observations, the influence of this poor start value is negligible. The duration for which the initial level has influence on the one step ahead forecast depends on alpha. A smaller alpha would be a longer duration, a larger alpha would be a shorter duration. Excel's solver can be used to find the optimal values for alpha and initial level. Click Data, Solver. The cell addresses, constraints, and settings for Solver have been stored in the workbook, so no changes are necessary. Solver will minimize cell G7, the SSC, by varying cells G3, the alpha, and G4, the initial level. The solving method is GRG nonlinear. Evolutionary can also be used, but it is slower. Click Solve. The Solver Results dialog shows that a solution has been found. Click OK. The SSC is now 19.74. Alpha value equals 0.295, and initial level is 16.732. By minimizing the residual sum of squares error, we have our best estimate of the parameters to produce one step ahead forecast values. We will now produce the ACF and PACF plots for the residuals. Click anywhere on the data table and click SigmaXL, Time Series Forecasting, Autocorrelation, ACF, PACF plots. Select Use Entire Data Table and click Next. Select Residuals E, click Numeric Time Series Data Y. Click OK. We can see that all of the autocorrelation has been removed by the simple exponential smoothing model, with the exception of lag 15 in the PACF. So this is a good fit to the time series data. By way of comparison, these are the ACF and PACF plots for the original concentration data, which are autocorrelated. Now, we'll have a quick look at the residuals using a histogram. Select the Sheet 1 tab. Click SigmaXL, Graphical Tools, Histograms and Descriptive Statistics. Select Residuals E and click Numeric Data Variables Y. Click OK. The residuals are normally distributed, with no obvious extreme outliers. Using the same Series A data from Box and Jenkins, the Exponential Smoothing Forecast tool will perform these calculations automatically. Click SigmaXL, Time Series Forecasting, Exponential Smoothing Forecast, Forecast. The number of forecast periods are the number of time series values to be predicted, the forecast horizon. The most accurate forecast will be for the first predicted value, one step ahead. The prediction interval percent is the confidence level for the individual predictions. For example, a 95% prediction interval contains a range of values which should include the actual future value with 95% probability. The interval will get larger the further out you predict. Model Options opens a dialog which allows you to set automatic options or to specify a model. Display ACF, PACF, and LB option will produce the ACF and PACF plots for the raw data, as well as for the model residuals. The LB plot is a plot of Young box test p-values for various lags and is used to determine if a group of autocorrelations are significant. Display residual plots will produce a table of model residuals and the usual model residual plots. Select Concentration and click Numeric Time Series Data Y. Check Display ACF, PACF, LB plots, and Display Residual plots. Leave specify model periods, seasonal frequency, and Box-Cox transformation unchecked. We will use the default number of forecast periods of 24 and the prediction interval of 95%. Click Model Options. Here you can choose either automatic model selection or to specify a model. Automatic allows you to choose one of the following model selection criterions: Akaike information criterion with small sample size correction, Akaike information criterion, or Bayesian information criterion. For more information regarding the automatic model selection criterion, see the SigmaXL version 9 workbook. Click Specify Model. This allows you to manually specify the error trend seasonal model. Seasonal options are grayed out because the seasonal frequency option in the main dialog is unchecked. A summary description of the model is also given. We will use the error additive trend none defaults. Simple exponential smoothing with additive errors, short form ANN, exponentially weighted moving average. Click OK. Clicking OK again will produce the exponential smoothing forecast chart. This is very similar to the simple exponential smoothing plot demonstrated before. It shows the raw concentration data in black and the one step ahead forecast values are in red, but with the addition of a 24-period forecast and the 95% prediction interval. You can zoom in to view the last 30 points on the forecast chart, which includes the predicted values. Click SigmaXL Chart Tools, Show Last 30 Data Points. To restore the chart, click Show All Data Points. You can also scroll through the data. Click Enable Scrolling. When prompted, click OK. The scroll dialog appears, allowing you to specify the start period and the window width. At any point, you can click Restore, Show All Data Points, or Freeze Chart. Freezing the chart will remove the scroll and unload the dialog. The scroll dialog will also unload if you change worksheets. Click Restore, Show All Data Points. Click Cancel to close the dialog. Now, we will look at the report. Scroll down to view the exponential smoothing model header. The model, Simple Exponential Smoothing with Additive Errors, shorthand ANN, Exponentially Weighted Moving Average EWMA, is the user-specified model. This is the same model information that was displayed in the model selection dialog. The exponential smoothing model information is a summary of model information. Here we can see seasonal frequency equals 1, non-seasonal, model selection criterion equals specified because the model was user-specified, and Box-Cox transformation is not applicable because Box-Cox transformation was unchecked. The parameter estimates closely match those obtained earlier in the demonstration using Solver. The slight differences in parameter results are due to differences in the optimization method. In the exponential smoothing model statistics box, we can see that the results closely match those obtained in the demo using Solver. The in-sample forecast accuracy metrics are shown. SigmaXL uses the following forecast accuracy metrics: root mean squared error, RMSE, mean absolute error, MAE, mean absolute percentage error, MAPE, and mean absolute scaled error, MASE. MASE is less than 1, so it is a better forecast than would be obtained from a naive forecast. The results once again closely match those given in the demonstration using Solver. The forecast table is the same forecast and prediction interval values displayed on the forecast chart. It's provided for further analysis or charting. Click on the Exponential Smoothing ACF PACF LB sheet. These match the plots that were obtained previously in the ACF plots for residuals. We can see that all the autocorrelation has been removed by the exponential smoothing model, with the exception of lag 15 in the PACF. The LB plot is a plot of Young box test p-values for various lags and is used to determine if a group of autocorrelations are significant. For example, The autocorrelations do not come from a white noise series. The red p-values are significant at alpha of 0.05, and the blue p-values are not significant. It is desirable that all p-values be in blue. The ACF PACF plots indicated that almost all of the correlation has been accounted for in the model, but the Young box plot shows that some significant autocorrelation still remains, so the model can potentially be improved. This does not mean that the model is a bad model. It can still be very useful for prediction purposes, but the prediction intervals may not provide accurate coverage. For more details, please refer to the SigmaXL workbook. Click on the Exponential Smoothing Residuals sheet to view the residual plots. These residual plots are the same as used in SigmaXL's multiple regression, which we cover in another video. The histogram matches what we obtained in the demo. The residuals are approximately normally distributed, with a roughly straight line on the normal probability plot. There are no obvious extreme outliers or patterns in the charts. In a later video, we will apply a control chart to the residuals to formally test significant outliers or assignable causes. Now, I'll rerun exponential smoothing on the concentration data, but use automatic model selection. Click Recall SigmaXL dialog menu. Click Model Options. Select Automatic Model Selection. For this run, I'll use the default model selection criterion, AICC, or Archaic Information Criterion, with small sample size correction. Clicking OK will return us to the Exponential Smoothing Forecast dialog. Click OK again, and the Exponential Smoothing Forecast report will be shown. Note the Exponential Smoothing model header. The model, Simple Exponential Smoothing with Multiplicative Errors, short form MNN, was selected as the best fit for the concentration data based on the AICC criterion. The point forecasts produced by the multiplicative and additive models are identical if they use the same smoothing parameter values. Multiplicative will, however, generate different prediction intervals to accommodate change in variance. The exponential smoothing model information shows the seasonal frequency of 1, but now shows the model selection criterion as AICC. Box-Cox transformation is not applicable because Box-Cox transformation was unchecked. The parameter estimates table shows an alpha coefficient of 0.30 and an initial level of 16.74, which are fairly close to the parameter estimates obtained using the additive model. The exponential smoothing model statistics are also shown. The log likelihood, AICC, AIC, and BIC are close to the values obtained using the additive model, but the log likelihood is slightly higher, giving a lower AICC, so multiplicative was selected as the best model. Note that the standard deviation and variance are very different. This difference is due to the multiplicative residuals being relative errors. The in-sample forecast accuracy metrics, forecast table, and ACF, PACF, and LB plots for multiplicative are also very close to the additive model. The multiplicative residual plots look the same, but note the different scale due to the relative errors. Now I'll rerun exponential smoothing on the concentration data with automatic model selection, but I'll also use specify withhold periods in order to obtain out-of-sample forecast accuracy metrics. Click Recall SigmaXL dialog, or press F3, check Specify Model Periods. The Specify Model Periods option allows you to specify the start and end periods used in automatic model identification and parameter estimation. Typically, start model at period is kept at 1, and withhold period specifies the number of periods to be withheld for out-of-sample testing. End model at period specifies the end period, so the withhold sample size would be the total number of observations minus the end period. Withhold forecast type, one step ahead, will exclude the withhold sample from automatic model identification and parameter estimation, but uses the withhold data to update the predicted one step ahead forecast. This is useful to assess forecast error when you only care about the short-term one step ahead prediction. Withhold forecast type multi-step ahead with prediction interval at start of withhold will exclude the withhold sample from automatic model identification and parameter estimation, and does not use the withhold data to update the predicted one-step ahead forecast. This is useful to assess forecast error when you're interested in the long-term forecast window, the forecast horizon. This will be demonstrated in a later video. I'll set the withhold periods to 24. We will forecast 24 periods and compare against the withheld actual. We will use the default withhold forecast type, one step ahead with prediction interval at start of withhold. Click Model Options. Select Automatic Model Selection. We will use the default model selection criterion, AICC, with small sample size correction. Click OK to return to the Exponential Smoothing Forecast dialog. Click OK. The Exponential Smoothing Forecast report is shown. The blank dots are the data values in the withhold sample, with the one-step ahead forecast and prediction intervals displayed at the start of the withhold sample. Scroll down to view the Exponential Smoothing model header. As with the complete data, the model Simple Exponential Smoothing with Multiplicative Errors, or MNN, was selected as the best fit for the concentration data based on the AICC criterion. The header also includes the number of specified withhold periods. The parameter estimates are close to the parameter estimates obtained when using all data in the multiplicative model. The exponential smoothing model statistics are also fairly close to the model statistics obtained in the previous results. However, note here we are only using 173 of the 197 total observations. This is because 24 withhold periods were specified, which are represented as the blank points in the chart. As expected, the forecast accuracy metrics for the out-of-sample withhold one-step ahead forecast errors are larger than the in-sample estimation one-step ahead forecast errors. The out-of-sample forecast is a better estimate of real-world forecast accuracy. In the forecast table, we can see that these are the same forecast and prediction interval values displayed in the forecast chart. They are provided for further analysis or charting. The withhold data is also displayed. This concludes part 1 of the Introduction to Time Series Forecasting video. For more videos, visit us at www.sigmaxl.com or join us on YouTube. Thank you for watching.